Welcome to the Deep Dive. Today we're kicking off a brand new series, actually. We're diving headfirst into ISO 26262.
That's right, the big one. The International Standard for Functional Safety in Road Vehicles.
Exactly. And this standard, well, it's basically the foundation, the bedrock of how safety gets engineered into our cars. So for this first deep dive in the series, our mission is pretty straightforward.
Laying the groundwork.
Precisely. We want to get everyone comfortable with the core language, the key vocabulary, and give you a bird's eye view of all 12 parts of the standard.
And then in the next few deep dives, we'll really get into the nitty-gritty of each part.
You got it. So let's start at the top. ISO 26262. Where did it come from?
Well, fundamentally, it's an adaptation. It comes from a broader industrial safety standard, IEC 61508, which has been around for a while.
Okay, so it's built on something established.
Yes, but it's specifically tailored, really meticulously adapted for the unique challenges of electrical and electronic systems, E-systems, in cars. And the key thing is it covers the entire safety life cycle.
The entire thing. From cradle to grave, so to speak.
Absolutely. From the initial concept through development, production, when the car is actually being used, service, and even decommissioning at the end of its life.
Okay, so it's incredibly comprehensive. Let's unpack this a bit.
Yeah.
What is it fundamentally trying to do? What's the main goal?
Good question. The standard itself actually lays out 5 key objectives pretty clearly. First off, it gives us a reference, a roadmap really, for the automotive safety life cycle. It guides all the safety work needed during, development, production, operation.
Service, decommissioning, all those phases you mentioned.
Right. Second, it provides a very specific, automotive-focused, risk-based approach to figure out how safe things need to be. These are the automotive safety integrity levels, or ASILs.
ASILs. Okay, we're definitely going to need to dig into those. So it's about measuring risk.
Measuring, classifying risk, yes. Which leads to the third objective, using those ASILs to specify which requirements from the standard need to be applied to avoid unreasonable residual risk.
So higher risk means stricter rules apply.
Exactly. The higher the ASIL, the tougher the requirements. Fourth, it sets out detailed requirements for managing functional safety itself, the design, the implementation, verification, validation, all that.
The actual engineering work.
The engineering and the processes around it. And finally, number 5, which is super important today, it establishes requirements for how customers and suppliers work together.
The supply chain aspect. Makes sense. Cars are built from parts from everywhere.
Precisely. It ensures safety doesn't get lost or compromised just because different companies are involved. It keeps everyone on the same safety page.
That is incredibly thorough. It really paints a picture of safety being woven into the entire process, not just bolted on at the end. And it directly impacts, well, you listening every time you drive, ensuring those critical systems, brakes, steering, airbags, meet these tough standards.
It's all about minimizing risk, right down to the code and the circuits. But it's also a huge balancing act for manufacturers achieving that safety versus the cost and effort, especially for the really critical stuff.
Okay, before we get lost in the details of how they do that, let's get our terms straight. Part 1 of the standard is just vocabulary. We need to speak the same language here.
Absolutely critical. Ambiguity is the enemy of safety. So let's start with functional safety itself. What is it? It's the absence of unreasonable risk.
Unreasonable risk.
Due to hazards caused by malfunctioning EE systems, basically preventing harm when the electronics don't behave as expected.
Okay, so if the car's computer glitches, it shouldn't cause harm. What's a hazard then in this context?
A hazard is simply a potential source of that harm caused by the malfunction. Now, there's a key sequence to understand. Fault, error, failure.
Okay, like dominoes.
Sort of. A fault is the root cause. Think a tiny defect in a sensor, maybe a software bug, a short circuit.
The initial problem.
Right. That fault can then lead to an error. The error is the manifestation, the system deviating from what it's supposed to do. So the faulty sensor sends a slightly wrong signal, maybe.
The system acting weird because of the fault?
Exactly. And that error, if it's not caught or corrected, could then lead to a failure. That's the loss of the intended function, or behaving in a way that might cause a hazard, like, unintended acceleration because of that sensor error.
Got it. Error causes potential failure, which leads to the hazard, and this all ties into risk.
Precisely. Risk combines the likelihood of that harm happening and how severe the harm would be. The whole point of ISO 26262 is to get that risk down to an acceptable level.
And how do they define acceptable?
Through safety goals. These are the top-level requirements that come out of that hazard analysis. Each one gets an ASIL assigned, defining what the system must do to be safe.
Okay, so we have goals. How are they achieved technically?
Through safety mechanisms. These are the technical solutions, hardware or software, designed to detect faults, prevent them from causing failures, or control the system to maintain safety.
Like a backup system.
Could be. Or diagnostic checks, redundant components. Their job is to achieve or maintain a safe state. That's a predefined condition the system goes into when a fault happens to ensure safety. Think limb home mode, or maybe power steering reverting to manual if it fails.
Instead of just stopping working or going haywire.
Exactly. We also need to think about dependent failures. These are tricky. They aren't independent events. A common cause failure is when one root cause takes out multiple things, like a power surge affecting several components.
Okay.
Or a cascading failure, where one component failing directly causes another one to fail. These are different from independent failures, where things fail for unrelated reasons, like a flat tire and a blown fuse.
It's clear why precise language is so vital. You can't build safe systems collaboratively without everyone agreeing on what fault or risk actually means. It standardizes everything. All right, now for the part that sounds really central. ASIL, Automotive Safety Integrity Level. You mentioned it's like a risk compass. This feels key.
It absolutely is key. ASIL is the risk classification system within ISO 26262. It defines the level of safety integrity needed for a component or function. How critical is it?
And there are different levels.
Yes, 4 main levels. ASIL A is the lowest safety requirement, then B, then C, and ASIL D is the highest, demanding the most rigor. There's also QM, quality management. That's for things where a malfunction doesn't really cause direct physical harm, so standard quality processes are enough. You don't need the full functional safety treatment. Think maybe the infotainment system map freezing, annoying, but not directly hazardous in the same way brake failure is.
Gotcha. So what does assigning an ASIL actually do? What's its purpose?
Well, it tells engineers how critical the function is, obviously, but more practically, it dictates the level of effort required in development. Design, implementation, testing, documentation, everything gets more rigorous, more scrutinized, often needing more independent checks as you go up from ASIL A to D.
More hoops to jump through for higher ASILs.
Essentially, yes. And this ASIL is determined during the HARE, the hazard analysis and risk assessment. It's a systematic process using 3 parameters.
Okay, what are they?
First is severity, S. How bad are the potential injuries? S1 is light moderate. S2 is severe but survivable. S3 is life-threatening or fatal.
Makes sense. Severity. What's next?
Second, exposure, E. How often is the vehicle in a situation where this hazard could occur? E1 is very rare. E4 is very frequent.
Okay, frequency. And the third?
Third is controllability, C. If the hazard occurs, can the driver typically control the vehicle to prevent harm? C1 is easy to control. C2 is normally controllable. C3 is difficult or impossible to control.
Severity, exposure, controllability. SEC.
Exactly. And you combine these according to a table in the standard. For example, a worst-case scenario. S3, life-threatening. E4, happens often. C3, driver can't control it. That combination points directly to ASIL D.
Highest level.
The highest, whereas something like S1, minor injury, E1, rarely happens, C1, easy to control, that would likely end up as QM. It's a structured way to assess the risk.
This really explains why, your anti-lock brakes feel incredibly reliable and have backups.
That's your classic ASIL D system.
While the navigation system might occasionally need a reboot.
That's likely QM. Other examples. Adaptive cruise control or power steering might be ASIL C. Headlights, maybe ASIL A or B. It depends on the specific failure mode and its potential consequences.
Okay, that framework makes a lot of sense. But developing an ASIL D system sounds intense.
Yeah.
And expensive. Is there a way to manage that complexity?
Yes, and this is a really important concept. ASIL decomposition. It's a strategy the standard allows. You can take a safety requirement with a high ASIL, say ASIL D,
Right.
and break it down or decompose it into multiple independent requirements with lower ASILs, maybe 2 independent ASIL B requirements.
So 2 less complex things replace 1 super complex thing.
Essentially, yes. As long as they're truly independent and together achieve the original ASIL D goal, this can make development more manageable, potentially use less complex hardware, and importantly, build in redundancy. If one ASIL B part fails, the other can still ensure safety.
So it's a way to build in robustness through redundancy while managing the development burden. That's clever. It suggests that sometimes distributing the safety task across simpler, independent parts is better than relying on one perfect, complex component.
It's a key strategy for preventing single points of failure in critical systems.
So we've covered the purpose, the language, the risk assessment with ASIL. What else is in this standard? You mentioned 12 parts. This sounds like a huge undertaking.
It is comprehensive. So we've hit part 1, vocabulary. Part 2 is management of functional safety. Think organizational stuff, safety culture, plans, roles like the safety manager.
The process infrastructure.
Exactly. Part 3 is the concept phase. That's where the HRA happens, defining the system, setting those initial safety goals. Part 4 is system level development, allocating requirements, designing the technical safety concept, system architecture, validation.
Bringing the concept to life at the system level.
Right. Part 5 dives into hardware development, specific hardware safety requirements, analysis methods like FMETA, and those fault metrics, SPFM for single point faults, LFM for latent faults.
Measuring hardware reliability against safety goals.
You got it. Part 6 is the counterpart, software development. Requirements, architecture, coding standards like MIS-RSE, testing, tool qualification. Hugely important. Part 6 is the counterpart. Part 7 covers production and operation. Safety doesn't stop when the car leaves the factory. This covers manufacturing, service, repairs, decommissioning.
The whole life cycle continues.
Absolutely. Part 8 deals with supporting processes. Things like change management, documentation, configuration management, the glue holding it all together. Part 9 goes deeper into ASIL and safety analyses. More on decomposition, analyzing dependent failures, methods like fault tree analysis.
More advanced analysis techniques.
Yes. Part 10 is different. It's guidelines. Not strict rules, but helpful examples and interpretations. Non-normative. Part 11 is crucial now. Semiconductors. Applying the standard specifically to complex chips like MCUs, SoCs, especially vital for ADAS and autonomous tech.
Addressing the brain components.
Pretty much. And finally, Part 12 provides specific guidance for motorcycles, adapting the principles for two-wheelers.
Wow. Okay, that is a lot. It really drives home that this isn't just a checklist. It's a complete systematic philosophy for building safety into vehicles from the ground up and keeping it there.
It's truly holistic.
So to wrap up this first deep dive, we've seen ISO 26262 is the automotive-specific adaptation of a broader safety standard. We've learned some key safety language: fault, error, failure, hazard, risk. We've understood ASILs as the core risk assessment tool, and we've glimpsed the massive scope of the full 12-part standard.
And understanding these basics is really valuable, whether you're developing these systems, regulating them, or just someone driving a modern car and wanting to appreciate the safety engineering involved.
Definitely. It leaves me with a thought, though, thinking about controllability, that C factor in ASILs. As cars become more autonomous, making decisions for the driver, how does that change our idea of controllability? If the car is supposed to handle the situation, does the driver's ability to control it still matter in the same way for the risk assessment?
That's a fascinating question, and one the industry is actively grappling with as we move towards higher levels of automation. It definitely poses challenges for future versions of the standard.
Something for all of us to think about. We've only scratched the surface today, of course. So stay curious. We'll be back soon to dive deeper into the specific parts of ISO 26262. Make sure you follow along for the next part of this deep dive. Thanks for joining us.